KIAC AML Center seminar series in the Department of ECE. So we're very happy to have Professor Al Bovik from the University of Texas at Austin at this point, right?
Yeah.
Visiting us today. So Professor Bovik is really distinguished. He's worked on several aspects of research at the intersection of vision science and picture quality, picture and video quality. And he's won several awards. He had the IEEE Edison Medal. He's a two-time Emmy Award winner and numerous paper awards in Signal Processing Society and Circuits and Systems for Video Systems Society. So without further ado, I'd like to welcome Professor Bovik. So Professor Bovik was my advisor. It was fantastic to work with him during my PhD, and I'm sure he'll have lots of interesting insights to share today with us.
Okay, thank you. By the way, I was here about 24 years ago or something like that. I was confusing the two campuses I'm visiting, but yeah, so I barely remember from back then. So I'm glad to be here. Thank you for having me the second time. I even forget the conference that it was the first time, some computer vision conference. So I'm going to be talking about, well, the title of the talk is Secrets of Video Quality. And the idea is to convey, why rather than just doing. Okay, these days there's a tendency to do things, meaning take an architecture, a deep architecture, put it together, go get a database, train it on there using some loss function, and there you've solved the problem, okay? But you don't really know the secrets inside that box. Why did this work, okay? So the problem that we're addressing in picture quality or video quality is a more human problem, okay? Because we're trying to understand when you look at a picture, why do you think it's of high or low quality? It's a very personal thing, really. It's much more complicated than, in many ways, has so many dimensions to it. Different people may agree or disagree what the quality of a picture is. And so the approach I'm going to take is, well, we actually do understand to a degree why we think the quality of a picture is what it is. Okay? It's not just the output of a box. Now, I'm not really going to talk too much about deep learning in this talk. Tomorrow I'll be at the conference, and I'll be talking more about deep learning there. I'll be talking about diffusion models and that sort of thing, but not today. I think today we're going to stick to what's going on inside our heads and what we can actually model using the old tools of statistics, mathematics, and visual neuroscience. Okay, so once I get it working. There we go. This is one of my favorite pictures ever. It was taken by a student in one of my classes as part of a homework assignment. The assignment was simply go out and take pictures, okay, as you normally would. Go out and have fun with your smartphone and take pictures. And this is a great picture because it's so dynamic. It shows people having fun. It's in a place in Austin called 6th Street, where all the students go to have fun, in the evening and that sort of thing. And when you look at the picture, I wouldn't change this in any way. I think it's perfect, which kind of shows the complexity of this problem. But yet I can also look at it as an engineer, a video engineer, a picture engineer, and say, there's all kinds of things that are technically wrong with this picture. It's all kinds of distortions. And so when I'm teaching my class, I'll show them this very picture, and I'll say, how many distortions can you find in here? And so people raise their hands and so on. And I took a pencil and I wrote down very quickly like 10 different distortions that are technically here. You can find all kinds of blurs from defocus at various depths, according to the depth of the field, motion blur, a blur from saturation. There's a lot of different kinds of blurs, overexposure, underexposure in various areas, compression artifacts, low light noise. You can find places where there's a little bit speckly, like under his chin here and so on. Red eye, very obvious. Lots of distortions, and you could make longer lists, but then there's combinations of all these distortions. Okay, and anytime you have two distortions and they combine, they've created a new distortion. which you don't even have a name for. Okay, and as I was telling these guys a few minutes ago, I think that really there's an infinity of distortions. The idea of taking an image and classifying the distortions, well, you can say that there's red eye and blur and that sort of thing, but in terms of trying to predict its perceptual effects, you have to recognize you can't just categorize it and say it's as simple as that, and therefore the quality is this. Okay? People tried that for 50 years. They tried to model distortions. They tried to model the blur in any picture taken with any device, and they would then try to predict how a human would say its quality was, and they would fail, generally. So the answer, the secret that I'm going to tell you is, well, it's not that way to do it. You don't try to model every distortion in the world because there's an infinity of them. Instead, you try to model how we perceive distortions at the neural level in the brain. Okay? So, why is this an important problem? Well, it's been around since cameras have been around. Thomas Edison, who made the first motion pictures, was worried about the quality of what he was purveying to the public way back in the early part of the last century. These questions are very important. Well, today, more so than ever, because most of our internet traffic is pictures and videos. 80%, approximately, of all that traffic is visual information. And why is that? Well, because we're the receivers. Humans are, and we're visual creatures. More than half of our brain is implicated in vision. Okay? We care about what we see, as long as we're normally sighted. Okay? And as I've said, all sorts of kinds of distortions. These are very common names. There's other ones as well that many companies now that purvey pictures in various forms and so on. And they're always worried about sending it from point A to point B. And the question is, well, when it arrives, what is the quality? What will their customers say? These distortions that can occur, as I've already said, can be very complicated, very hard to disentangle, very hard to understand, but they definitely affect user experience. If you're watching a television show that's distorted, you may change the channel because you want to watch something that looks good. And consumers are increasingly demanding in that regard. But it also affects things like bandwidth usage. If 80% of all the bits on the internet are pictures and videos, they're gobbling gigantic amounts of bandwidth. Okay, that affects our environment. In fact, the internet now is like between 5 and 10% of the carbon footprint, okay, of everything that humans do. And it's increasing. And that means that videos are about 80% of that because of all the compression, the computation, the wireless cell towers that are broadcasting with tremendous power to reach everybody. Okay? If you can transmit fewer bits, then that's better. Okay, so I'm going to be talking mostly today about what we call high-quality content, cinematic content. Things you can go to the movies and expect to see because professionals capture the pictures, the videos, the movies, and they are the ones who created the content. There is another category called user-generated content, and that's pictures that you guys take, or like the picture I showed you earlier. But I think a good starting point is to start out with understanding high-quality content and how it's distorted by various processes such as transmission. Okay? Here's a typical video communication system for today, for that kind of content. There's a transmitter, a channel, and a receiver. Now, when I was in school, we all studied communication theory, and to understand communication theory, you would study the transmitter, the channel, and the receiver. And the better you understood each of those three things, the better job you could do of creating a communication system. Okay? Same thing with video. Okay? Except now, the transmitter is not the classical one, an antenna, or something like that. Even in the internet age, some sort of package-producing entity. Instead, it's the real world of photons and how they interact and are captured by cameras or our eyeballs. That is the transmitter. Okay, so we'd like to be able to model that to do a better job of visual communication. And the receiver is, again, not an antenna, It's the visual brain and the eyeballs and the visual pathway. Okay? These are the kinds of things that we have to model. What happens in between is everything else, which is all these various sources of distortion. Distortion, all these blinking red arrows, can happen everywhere throughout the internet. There's all kinds of distortions in the capture device, where it might be blurry or something. The display device, which is imperfect. Okay? The channel itself, there's things like packet loss. And the providers, all of these streaming and social media companies, they process the videos. They compress them, they resize them, they do all kinds of things so that they can squeeze it down that channel to get to you so you can watch it. And when they do that, they're distorting it. And there's even distortion in our brains. There's something called neural noise. There's imperfect optics. So, video quality. I've already mentioned that there's a lot of different kinds of distortions that can occur. This is just a short list of names of these. But once again, they often coincide and create new distortions. And trying to name all the distortions and then go find each particular named distortion using some model has not proven to be effective or feasible. Okay? Whether spatial artifacts, things like the blur or noise that you typically see, or temporal artifacts. And later today, I'm going to be talking about temporal or time evolving artifacts that are very powerful in terms of determining the quality of the video, the movie, whatever it is that you're watching on television or whatever. Many things that you could list, but once again, it's pretty fruitless to try to create, distortion-specific measurements. Try to measure, the exposure level, from the picture and that sort of thing. Just doesn't work. Okay? Yes.
Judder?
Judder? Well, that's actually an artifact from something called 3-2 pull down. Okay, from the old days of when we had interlaced videos. Okay, and so what would happen with 3-2 pull down, you want to convert it to something that's progressive. Instead of having just even and odd lines like old television, you want to have every line present in every display. Okay, and there's a process where you would repeat the even ones 3 times and the odd ones 2 times, and it creates this bit of a discontinuous effect when you view it over time. Okay, so stutter is something similar, but I'll be talking about that actually today, and that's simpler. Okay. All right, so I hope I've conveyed the impression that video quality prediction seems like it's a very hard problem. Just there's so many distortions, so many contents that can be distorted in so many different ways and levels of distortion. It might be a very gentle distortion, a very severe distortion, everything in between. How possibly can you predict it when you've got all of these distortions coexisting? Okay, well, the answer is, again, not modeling the distortion itself, but actually modeling the transmitter and the receiver. And we can do that because videos are special. They have special properties. When I say special properties, what do I mean? Well, actually, they obey certain statistical laws, invariably. If you have a high-quality camera and take a high-quality picture, capture it and record it, it's going to obey statistical laws, which is not something anybody really ever expected to be true, that they obey laws. After all, if you take a picture, it can be bright, it can be dark. If you plot its histogram, if anybody knows what that is, frequency of occurrence of the brightnesses or colors, it can take any shape. It's totally unpredictable. But underlying all that, following some very simple perceptual processes that we can model mathematically, we can reveal these statistical properties. Okay. And that's without even human brains involved. Okay. Videos, if there was a camera and no humans, it would record videos that have these special properties. Now, obviously, human eyeballs have been exposed to the world of visual information, which is sort of a video on your retina, right, over the eons, and they have adapted to exploit the special properties of videos, to understand them, but also to react and understand or to perceive the quality of them. Okay, so I'm going to go through just a few. There's actually a pretty long list of very special properties that videos enjoy. Okay, the first one is one you may actually have heard of, even if you aren't a person studying video. You may have heard of the 1/F law. they often call it. Okay? If you have a video, and here I'm keeping it simple, it's just a picture. This is its spatial or temporal frequency. It's a Fourier transform. What's that? Okay. Well, I can't teach you what a Fourier transform is here, but I will make an effort to explain something in a little while. Okay. If we look at what's called the power spectrum, the expected transform magnitude, it falls off with frequencies. The frequency increases, then the amount of that frequency decreases like a 1 over f. Okay, and videos obey this pretty darn well. It's one of the weaker properties I'm going to talk about, actually. So I guess I can stand here sort of and operate this. Okay. When I say 1 over f, I don't mean literally that alpha is equal 1, which it often is approximated as. But if we actually do empirical studies, we find that the exponent in both space and time is around 1.2. Okay, so if you take a lot of different pictures and take the Fourier transforms and measure their drop-off, on average, it's around 1.2. Okay. Here's an example, just one picture, but the picture is a video, and so it's changing over time. And I'm just showing you it came up very nicely. On the left here, this is the spatial power spectrum on a logarithmic scale. Okay, now because it's on a logarithmic scale, any differences from linear are actually magnified. So actually, this is a pretty linear on a log scale, which means it's a nice 1 over f on a linear scale. This is the temporal spectrum, and notice the video is changing rapidly. Okay, you're seeing different scenes because the sled is bouncing around everywhere, but the plot looks the same pretty much. And that place where it goes is just because of a endpoint, the wraparound of the video. Okay, so it's a discontinuity, an artifice. So this has certain implications. If a function has a 1 over f type of spectrum, then it is unique amongst functions in that it has a self-similarity property. Meaning if you scale the Fourier transform, then it scales the transform function in a unique way, a multiplicative way with the scaling factor. Only videos, only pictures, only signals that have this property have this property. Okay? And the person who first discovered this was a guy named Benoit Mandelbrot. You remember him? Mandelbrot used to be, these guys will remember because fractals. Okay? He's the guy who developed the theory of fractals, self-similarity of our universe, of everything in it. Okay? And, you know, this is just a reflection of the Mandelbrot concepts that pictures of the world are self-similar. They have a multi-scale property. Okay? And by the way, our perception of them is also multi-scale. And I'll talk about that in a while. Okay. Second special property, you know, back in the late 90s, in science, there's often parallel thinking. There was a couple of vision scientists who had a unique idea. Okay, they had the idea. Well, suppose we look at a patch of a picture, a little piece of a picture, and they know all these engineers are analyzing the Fourier transforms and the discrete cosine transforms of those little patches of pictures. They had an idea. Well, what if we did something else? Okay, so they said, well, any piece of a video. Maybe it's just a frame of a video and you're taking a little block, okay? You can represent that as a linear combination of basis functions. This is basic linear algebra, right? And there's an infinite number of possibilities here depending on how you choose the basis functions. I went too fast. Back, fast viewed, forward. Okay, sorry, I didn't mean to press that one yet. So some examples of this are a discrete Fourier transform, where the basis functions are sinusoidal functions or complex exponentials of a discrete form, or the cosine transform, or you can try to find optimal basis functions with optimal weights for that function under a mean squared error criteria like this one. Does anybody know what that's called? If you've done any data science, you should know that. It's called principal components. The principal components are finding the optimal basis so that the basis functions are actually decorrelated and satisfy minimum mean squared error criteria. Okay? Well, these guys went a step further, and they said, well, we've tried PCA on images, and it's not very revealing. It just shows sine wave basis functions. Okay, it's just like the Fourier transform, cosine transform. They said instead, what if we instead impose an extra constraint on it, which today we call it a sparsity constraint, where we force the coefficients, okay, to minimize a certain functional, extra function. Now, the kind of function they chose were functions that had creases in them. So here, like absolute x has a crease at the origin, okay, and log 1x plus squared. This is a higher dimensional creased function in 2 dimensions, where you see a crease along here. Maybe I'll use my pointer. A crease along here and a crease along here. And you can imagine optimizing this in an iterative way, and the solution kind of falls down into a crease and stays there. When that happens, one of these coefficients then is 0. And as you optimize, more of them are 0 until you just have a few that are not 0. Only a few basis functions are needed to represent that, and it's called a sparse solution. Okay? At the same time, a guy named Robert Tibshirani at Stanford was inventing the same idea in the statistics. It's called the lasso. Okay? Another thing you should know if you're studying data science is the lasso. Right? Okay? So what did they find with images? They found that with every image, the kind of basis functions they found look like these. Little waves. Little waves. Okay, what people used to call wavelets when wavelets was the big topic in signal processing and image processing. Oscillatory functions that are limited in space because they fall off. Now, interestingly, if you view these as functions that represent a linear system, then these are all what you call bandpass filters. Now, some of you probably haven't heard about bandpass filters, and I'm going to ask for a little help on that in a minute. Okay, what is a bandpass filter? But with every image they applied this to, they found the same form of basis functions. Little wavelets or little bandpass filters. Okay? So, for those that never have experienced what a bandpass filter is, if you're in computer science, you may not even have had a Fourier transform understanding. A bandpass filter is something that only allows a certain range of frequencies, in this case, spatial frequencies. Okay? But in making this talk, I said, how can I explain this in a simple way, what it is? And so I asked for some help from ChatGPT. Okay? Something I don't ordinarily do. And I said, explain a bandpass filter to a novice in 30 words. And I think ChatGPT did a pretty good job. It generated this exact sentence, and it says, highlights features within a certain size range, blocking details that are too large or too small. In other words, just letting whatever is in between be there. So in this image, there's features like the hands and the surround of the clock face and so on that are kind of intermediate range. But notice that the face of the clock and the background are now both intermediate gray. They've been sort of erased because they're too slow moving, too large, not fine enough. And I asked ChatGPT also to generate these 2 images with just a couple of sentences. I was pretty amazed at that point. Okay, generate a non-directional bandpass image of this clock. I supplied the clock, and there it was. And then I said a directional one. You can see small, it's not projecting very well here, I think, but you can see directional response here, especially to, these small features. Anyway, so the sparse features of images are bandpass functions. Now, I'm going to talk about the brain for a second, because vision scientists have been exploring the visual brain for a while. They've studied animals like cats and monkeys and actually made measurements, electrophysiological measurements of the responses of neurons in the retina, in visual cortex, and in the midbrain, the area called the thalamus, specific area called the lateral geniculate nucleus. And they have found that at the retina, the responses of certain cells called ganglionic cells are nicely approximated as linear systems having impulse responses that are bandpass and approximately circularly symmetric. And people who've studied computer vision in the past know that famous model called the difference of Gaussians model, which is used in things like SIFT and back in the old edge detector days and that sort of thing. In the midbrain, bandpass responses again, okay, which have center frequency somewhere in the range of available spatial frequencies. There's different neurons that have different center frequencies. So you get actually a set of filters, which in signal processing we call a filter bank. And in the back of the brain and primary cortex, we get directional bandpass filters, okay, that allow not only a range of frequencies from high frequency to low frequency, but also the direction of their propagation. Okay? These are called typically simple cells in visual cortex. This is in space, this is in time, this is in space. These are all in frequency. This is a bank of filters like these. Okay? This is our visual brain. Now, in the early days of CNN's post-2012, people were trying to understand deep networks as they were first finally available. And they found in the early layers of deep networks, when they were trained on something like ImageNet for visual tasks like recognition, they found that, golly, the weighting functions of those various layers, well, they looked like these things, okay? Directional bandpass filters. So deep networks are learning, without being told early on, to find sparse, efficient representations. So why is the visual brain and why are deep networks trying to find sparse representations? Because it's a way of obtaining visual information that is much richer, much denser, and doesn't take up as much space. In fact, there was a psychologist named Horace Barlow back in the 1960s. There wasn't much known yet about how the neurons in the retina in the back of the brain worked yet. The Nobel Prize-winning work of Granlund and Hartland on the retina and Hubel and Wiesel back here on modeling these hadn't happened yet. But he still realized the neurons in the front end of the visual system, because of the sheer volume of information that's coming into our brains, it must be simply for the purpose of reducing that information content without getting rid of the salient information, the important information. He called it his efficient coding hypothesis. And it has been proven over and over again, not only in vision science, but also in deep learning, the efficient coding hypothesis. Okay. Third property is the most important for us, but it builds on the other ones actually. And this one has an interesting history, which I'll explain in a minute. But a little bit of math here, a little bit of statistics. We can, if we take a video or a picture, or a three-dimensional picture for that matter, the dimensionality doesn't matter, space or time, and if we pass it through a bandpass filter, okay, to obtain a bandpass signal, okay, then because the input was an image, which has this following special property, we can model it using what's called a Gaussian scale mixture model, okay, which is a product of two random fields, one of which is a scalar variance random field, and the other basically just Gaussian noise. Product of Gaussian noise and structure, okay? So images obviously contain information, objects, outlines of objects, patterns, textures, everything. And this is embodied in the variance signal. This is the information signal that the brain actually uses to extract visual information and to recognize faces and people and so on. Same thing with deep networks. But what about the Gaussian noise? Why is that there? Why is that useful? How could that be used? Well, if you have an image or a video, you can actually estimate the variance field. You can just compute the sample variance over local regions, for example, and that is commonly done. Okay? Divide it out, or maybe condition on it statistically, and what you have left is just this noise. Is it useful? Nobody thought so, but turns out for what we're trying to do, it is what is useful. Okay. So you can actually, if you have a picture that's bandpass, if you represent it as a Gaussian scale mixture, you can actually write an expression for the density function. You can actually use that to make a maximum likelihood estimate of the local variance field using the samples that are observed, G, okay, these guys, and by estimating the local correlation structure of the image, and you can approximate it. But you can also do just about as good a job just by what I said. Estimate the local variance in space or time or both, or maybe even over scales. Okay. If you estimate this and then condition on it or divide it out, like I said before, and just repeating myself, you get something that is a Gaussian noise. So this was first discovered by a visual psychologist named Daniel Ruderman. He performed a very simple experiment where he went out in the woods, literally, out in nature with his camera, took many pictures, developed them, because this was back in the 80s before digital cameras were around, developed the pictures, okay, and then he digitized them. And then he performed a simple operation of analyzing the pictures on a local basis like any statistician would do. He would look at a local region of the picture, compute its mean, subtract it out, compute its standard deviation, divide by that, okay? And what he found was when he applied that to pictures, what was left was always Gaussian. It was always Gaussian. He didn't understand it, and it was published in the literature. It made very little impact for years. Now it's one of the, say, 3 foundations of all of vision science. And it's called the theory of natural scene statistics. That subtracting the mean is a bandpass operation, and dividing by the local standard deviation is just what I'm describing here. Okay. So here's a couple of examples, a couple of pictures. Bandpass filtered both of them and then divisively normalized them using this maximum likelihood estimate. This shows the histograms of the results, meaning the empirical probability mass functions. And, well, it's in a log scale, so Gaussian becomes this sort of linear thing. And it's superimposed on actual Gaussian. You can see the dotted lines there. You can't see it otherwise because it's such a perfect fit. Okay? So it's an amazing thing that people didn't suspect, that underlying all visual signals is this underlying Gaussianity. And nobody's been able to explain it. It's been studied by Nobel laureates and Fields medalists, and nobody can explain exactly why that is, or prove that it has to be that way. Okay? But it, nevertheless, is true, empirically, now over decades. So, if something is true about visual information that is entering the brain, the visual brain, then the brain must be using it somehow or another. And in fact, the brain is. I've already established that at the ganglion, at the retina, in the midbrain, and in the back of the brain, bandpass filtering occurs, which reveals part of this structure. But also, those neuronal structures are also subjected to what is called divisive normalization. So if this is a neuron, say in primary visual cortex in the back of your head, its output is divided by the energies of neighboring neurons, spatially neighboring neurons. Okay? Now, if they're spatially neighboring here, that's because they were spatially neighboring out in the world. The mapping of the visual world stays continuous and connected back here in visual cortex. It's been shown through various mapping functions where they actually slice it and show the responses of striate cortex. So in other words, the outputs are divided by neighbors, which is an approximation to the variance, really, the local variance structure. And we can do that also computationally. We can compute outputs of bandpass filters, call them wavelet filters, divide each by its neighbors, and what out comes is something that will look Gaussian if we have a good quality picture. Now, this kind of processing is a lot like layer normalization that is used in deep networks, discovered a few years ago. Gregory Hinton liked to do it, okay, early on. And it also explains certain perceptual illusions that are important in the context of picture quality. Masking processes specifically. I'll just show you an example so you can get it. Okay, here's a picture of a little girl. You can notice that she's distorted. You can see these little blocking artifacts all over her face and arms and so on. Okay, that's because it's been heavily compressed by an algorithm called JPEG, which you've no doubt heard of. Okay? But the JPEG is applied equally everywhere. And the amount of distortion is just as much everywhere. Okay, if you subtract this from the original, you get the same degree of differences. Okay, but you don't see the distortion out here. It's hidden, it's masked by the underlying content. And the way it's masked is, well, you're dividing by the local energies of the content everywhere, which sort of vanishes the distortion perceptually. Okay? So this process of divisive normalization actually explains this visual illusion. Now, doesn't that seem important if we're trying to predict quality? You know, I mean, here the quality is not so good because of the distortions, even if it's a nice, pretty little girl. Okay, the distortion is bad, but out here you don't notice really that distortion as much. So if you're going to create an algorithm that predicts quality of a picture or video, you need to account for this. Well, how can you create algorithms now? Okay, so I've described some very simple processes. Bandpass filter an image, maybe with many filters, or maybe with one. Divisively normalize all of those responses. And you're supposed to get something that looks Gaussian. But the amazing thing is, if you distort the pictures, then those statistical laws are broken. This is where the power of picture quality prediction comes. That's the main secret. So suppose we have a couple of images. One is an original and we distort it, say with JPEG compression. If we pass it through our perceptual processing model, bandpass filtering, divisive normalization, okay, just like happens in deep networks and in our brain, okay, then the output should have a Gaussian property if it's a good quality picture. It turns out if it's a low quality picture, then it doesn't come close to that Gaussianity. It falls outside of it. And you can think of maybe measuring the distance as a measure of quality. And that's precisely the kind of thing we're going to do. The distance, the statistical distance between the processed image that is distorted and the one that isn't is a measure of quality, perceptual quality. And so what we're really doing here is modeling quality at the level of the neuron. At the level of the neuron. Instead of trying, you notice I'm not saying here anything about, oh, let's estimate the amount of blur or the level of the noise or how many blocks are in the image from JPEG compression. Instead, I'm just talking about the distance from the ideal. Yes?
The local content needs to be normalized to get to the Gaussian, but there could be issues in estimating that and divide.
I haven't talked anything about estimating content because that's not needed. Okay, you literally, for whatever the content is, let me put it a different way. If I take 1 billion cameras, put them in different places in the world, take 1 billion pictures, and I take good pictures, mind you, okay, and I perform this simple perceptual process I've just described of bandpass processing. There's different kinds, of course. You can do a whole wavelet transform with many filters or just one filter, divisively normalize. The outcome will be Gaussian. I haven't had to worry about the content. In some sense, I've removed the content through that divisive normalization. Okay, so what's left is just this Gaussian property. Okay? People have a great deal of hard time understanding or agreeing with that possibility that if you process every picture this way, that what's left is Gaussian. But it is so. And people have been pondering this for decades, why this is so. Okay? Well, we don't know exactly why, but we know it's really useful for quality prediction. Okay? So again, I haven't mentioned content here at all because it's not required. We don't have to do any computer vision analysis, find objects, or anything like that. Okay? It's just very simple, low-level processing. In fact, if you think about it, picture quality perception is very low level. It's instantaneous. Okay, it's what we call precognitive. When you look at a picture, you see that it's blurry without any thought, without any passage of time. It's essentially instantaneous on a neurophysiological level. It happens in a few hundred milliseconds. Okay, so let's talk about how this is done and used now in the world. Okay. This basic idea of measuring this distance is used at the broadest scales by technology companies like Netflix, YouTube, Amazon. Basic idea, and again, remember we're talking about high quality video, okay? We call that the reference video, which they then subject to distortion processes, typically compression, scaling, that sort of thing, before they transmit it. They distort the video intentionally so that it can be sent with a much smaller bandwidth so it can eventually reach you. Okay? So to predict the quality of this video relative to this one, you need good models of the transmitter, the receiver, and well, these models are what we call duals, okay, because the transmitter has this underlying Gaussian law. The receiver is processing the video to reveal the underlying Gaussian law. Here's a basic model that we formulated in 2006. This is a spatial measure of information loss. Okay, suppose we have a reference frame and a distorted frame. Potentially we've compressed it or something. We perform a bandpass operation on it. In our case, we use what's called a steerable pyramid, very famous wavelet transform. We then estimate the local variance field using our maximum likelihood formulation from earlier, and we condition on it to compute the entropies. We compute conditional entropies. We also add a neural noise model, just additive noise, to model the uncertainty of the vision system. Turns out that's really important and really increases performance. So we actually calculate these conditional entropies. We scale them in certain ways. I'll talk about it in a minute. We pool them. We take differences and pool those, eventually coming up with a single number, which is a predictor of quality. Okay? It's just a difference between entropies, basically scaled entropies, but still an absolute difference between entropies. Okay. Then also, we do this in the temporal direction. So a simple way of accessing temporal information is just to take differences between two frames. This is frame at time t, t minus 1, just subtract them. Turns out differencing, if you've had your DSP class, is also a bandpass operation. The difference between 2 points in a signal, that's bandpass. It has a Fourier transform that's a sine pulse. Okay, very bandpass. But then the rest of this diagram is identical. Bandpass processing, conditioning, conditional entropies, scale them and pool them, producing, well, quality-aware temporal features. Okay? By the way, the guy who did this stuff is sitting up here. His name is Rajiv, Dr. Rajiv, okay? This could have been just taken directly from his dissertation. In fact, it basically is. Now, just to show the math a little bit, I'll go through this quickly, because I've been kind of going slow here. I think I'm a little jet lagged or something. But same model as before, Gaussian scale mixture model, the neural noise model. We estimate the variance fields for all of these signals. Remember, I showed you a frame and a frame difference and a distorted frame and a distorted frame difference. So there's a cross product of 4 different signals, all of which we apply the same perceptual processing to: wavelet transform, divisive normalization by the estimated variance field. And these are just the equations. Okay, I showed you this already. These are the conditional entropies, which you can calculate. This shows scaling by the log of the variance field. The idea here is if you have a lot of energy locally, the variance is high, it must be visually important. So it's a larger weight you're applying to those entropies, okay? If the entropy is very small, this approaches zero, this logarithm, and it's not given hardly any weight. Okay. So this basic idea is used in a number of algorithms. The first one was spatial only. It's called visual information fidelity. It's from way back when, okay? The second one is called space-time reduced entropy, space-time red, we call it. Okay, this was Rajiv's work, which was done about 10 years ago or so, okay? These ideas were then taken, the same features were taken by Netflix, who we worked with for about that amount of time, who created a model called visual multi-method fusion. They're using multiple features from these models, okay? They feed them into an SVM with another feature called a detail feature and a frame difference feature, okay? Basically using Rajiv's model and my former student Hamid Sheikh's model, okay, to predict visual quality. Now, Netflix now controls all of their encodes for many years now using this algorithm, okay? How much they compress every video. It's a very powerful idea because they want to push that compression as much as possible because, well, first of all, they want the internet to function properly so that it's not overloaded because Netflix was streaming 35% of all the bandwidth there for a while. Now YouTube is something like that, okay? Push the compression as much as possible just to the point where you still can't tell that it's compressed. And how do they do that? Well, every time you order up a show, like Stranger Things or something, there's like 20 versions of it that are created in the cloud or have been pre-created. Each one of those perceptually optimized for an expected level of bandwidth using this model I've been describing for the last 20, 30, 40 minutes, okay? At the largest scales. And now this model is used by many companies, like Amazon and YouTube and others as well, okay? Twitch, you name a company, they're probably using VMAF to compress and stream their content. Here's an example of it. This shows an ST-RED map, which is basically the same thing as VMAF, okay? So here's a high quality video. Here's one that's been compressed. You can see some compression distortions on there. I mean, this is kind of blurring it, this device. Not much activity here because the quality is high. Where you see the activity, this is where the local quality is being estimated as being a problem, lower quality. Okay? It's not obeying the Gaussian law in those places. Okay, so how's it being used? Okay, the basic idea is when there's a content, you want to compress it. This is an encoding engine like H.264 or HEVC. How much do you compress it? Well, you control that using the VMAF algorithm, okay? Compress it just that certain amount, depending on the network conditions, okay? It may be over wireless, over a wire, whatever, and it may appear at any kind of device. That can also be taken into account, okay? It's the device that decides based on the bandwidth conditions which one of those versions I always reach on the cloud, cloud's up there, which one of those versions to use on a per scene basis, okay? So this technology won an Emmy Award, and I think Rajiv has one. Where do you keep that, at home or your office? At home? At home. See, he's a humble guy, okay, but, okay. Okay, so I'm going to show you something newer, a newer use case, okay, and that is for what's coming next out there, which is high frame rate videos. Why is that? Why do we need high frame rates? Well, because of things like sports, okay? People running up and down back very quickly down the basketball course, so they're running back, running across the field, the soccer players, the football players, everybody. That's the biggest thing, and all of the big streaming companies are getting into sports now, okay? Amazon's getting into tennis big time. YouTube, football. Guess what Netflix is getting into? WWE. Yeah. If you call that a sport, I think it's more like theater. But anyway, there's fast action in that too. Okay, so I think some of us here remember 30 frame a second television, but of course these days we have 60 frame per second progressive digital television that we watch on all our large format screens, but 60 frames isn't enough if we're talking about really fast moving content. And they're really interested in this. And so this is why we did this study with YouTube. Let me go show you an example. I mentioned stutter a little while ago. So hopefully it'll show up on this. It kind of filters things. This is a scene where the camera is panning quickly. Oh. Yeah, no problem, no problem. Okay, so this is at 24 for a low frame rate. This is at a higher current frame rate, okay? Like I said, this is my travel laptop. You can see that it's very jerky, okay? That's called stutter. The camera's moving very quickly, and the number of frames per second is not enough to keep up with it. It's not a fast enough sampling rate. And that is visually very annoying because you have this stutter. Okay, you don't want that, that kind of thing happening when you're watching the guy running down the field. If you increase the frame rate, there's still a little bit of it, still maybe not enough frames. But you can see how much more smooth the presentation is. It's more pleasurable to watch. It's not annoying. It's higher quality. So now we're talking about a measurement of quality as relevant to high frame rates. Okay? So I went through a lot of discussion about the statistics of videos, what they ought to be if you have high quality, and what happens when you don't. Same thing here. Because we don't have enough frames, because the frame rate is too low, we're disrupting the natural statistic structure of images, which happen on a continuous basis as they're incident upon our retinas. They're violating the statistical law underlying it. So I'm going to look primarily in the temporal side here. And you're going to notice that I'm going to introduce something called a pseudo-reference, which I'll describe in a minute. Okay? We have a reference video, a distorted video, but we also introduce something called a pseudo-reference. Okay, and I'm just going to talk about this stuff. So, given a video, we bandpass filter it with a bunch of bandpass filters. Okay, we happen to use the Dobeshay bioorthogonal 2.2. They have very nice properties for representation of images and pictures. It used to be signal image processing imagers would know exactly the filter I'm talking about just 10 years ago. Now it's all deep learning. Okay, we're basically modeling the midbrain, an area of the thalamus called the LGN, okay, where these kinds of temporal bandpass filters actually occur. Okay, this is just an approximation to them. Banks of these filters. If we pass the same video through one of these bandpass filters, okay, you'll see that you can see that statistical chaoticness in the bandpass domain. Okay, this is at only 24 frames per second. It's really chaotic. Whereas at 60 frames per second, there still is some stutter that's creating some chaos. But once again, it's going to be a much smoother type of representation. Not perfect, but it's a lot better. Okay? So this is just a visualization of the statistical differences between these two videos along the time dimension. Again, though, it's all about that underlying Gaussian property. Okay. This plot shows the entropy versus frame rate. The same kind of entropy we've been computing. Okay. You'll notice that this is a higher frame rate down here. These are lower frame rates. At lower frame rates, we have a higher entropy, much more chaotic, right? Much more chaotic. At high frame rates, much lower entropy. And so the separation between these is actually one way of visualizing the differences in temporal quality of these videos. Okay? These videos aren't only affected, though, by the frame rate. They also have compression. Okay? And so all these videos are compressed. And we have to consider both, if we're considering the practical scenario of streaming to the world, both frame rate as well as amount of video compression. So to measure the spatial quality, we have to sort of remove this effect to then isolate the spatial quality. That's why we introduce the reference video, the distorted video, and now the pseudo-reference video. What is the pseudo-reference? Very simple. The reference is the original. The distorted is the one that has compression and possibly a different reduced frame rate. Okay? The pseudo-reference is just the reference that is sampled in the time dimension at the same reduced frame rate, but it's not compressed. Pseudo-reference, not compressed, but is compressed in the same way by too few frames. Okay? So we compute the same types of conditional entropies as before with scaling. Okay? Then we compute what we'll call a generalized space-time video quality features, okay, where there are differences in entropies and a ratio of entropies. The difference in entropies between the distorted video and the pseudo-reference, and the ratio between the true reference and the pseudo-reference. Now, why this particular functional formulation? I can explain it when we consider cases where there is no distortion, either from compression or from frame rate variation. Okay? So this portion measures the spatial distortion from compression, okay? Whereas this one measures the frame rate distortion. So for example, if the reference and distorted have the same frame rate, then the pseudo-reference does as well. The ratio term becomes equal to 1. And this is just the same kind of difference of entropies that we had in the original formulation. ST-red and VMAF and so on. Okay? If there is no compression, then the first term disappears, and you're left just with the ratio between the entropy of the reference and the pseudo-reference, okay, which measures the distortion from the frame rate distortion. Okay. And you only get a 0 when there isn't any distortion at all. No frame rate distortion, no compression type distortion. All right. Okay. So how do we use these features? Well, what you can do is you can take any video quality model, including VMAF, used throughout the industry, or maybe you've heard of structural similarity, SIM, also used extremely widely throughout industry. Those are kind of the two big ones. Or any other model that you might try. You can add these features, then train a simple shallow learner on the features from the VQA model and from the features I've just described, and on a database of human opinions of visual quality, of which there are ample numbers now. In particular, we have a database that's devoted to variable frame rates, from low frame rates, high frame rates, and so on. And you get tremendous improvements in results. So here's an example. This SIM and multi-scale SIM and VMAF are the three most widely used algorithms in the world in industry and by the deep learning community. SIM is used heavily to gauge how good a deep learning model denoised or deblurred or did whatever else. Okay? And you can see a huge leap in the correlations between the algorithm output and the human judgments on the huge, large database. A leap of about 0.2 or 0.3 translates to hundreds of billions of bits saved every year, because you can compress it that much further, because you've accurately gauged whether you should change, in this case, the frame rate. Now, this technology is still coming, where we actually have the streamers changing frame rates actively. They change compression parameters actively right now, even in real time, to achieve perceptually optimized delivery of the videos that you're watching at home that look so good. Okay? But the goal soon is to actually change the frame rates that are delivered to you using this kind of model. Okay? So that's a huge leap forward. Enormous bandwidth savings on high motion content by perceptual optimization. Okay? Now, interesting thing is, I'm almost done, by the way. Okay. Interesting thing is that if we look at the model like SIM and VMAF versus the improved one, each one with a GST in front is the improved model using our, generalized space-time features. You notice that it's especially at lower frame rates that the improvement becomes very large. Like VMAF has a very low correlation against human subjective judgment of quality at low frame rates. Whereas the new model is very high already. Okay? VMAF is very good when you have very high, very fast videos at 120 or 90 or 80 frames per second. Okay? But as the frame rate is reduced, then it falls apart. Okay? That's important because if you're watching videos where there isn't high motion, you'd like to reduce the frame rate a lot. Just imagine the bandwidth savings you can get from that. You're watching the news, the only thing moving is the guy's mouth, right? Okay? Hardly any motion. Whatever motion there is pretty slow moving. You can change the frame rate of that possibly, okay? Save a lot of bandwidth. So this is the way you could perceptually optimize that process. I have a second one, but I'm going to skip over this just because I've been kind of slower talker today. Again, jet lag probably. But just to summarize, for hundreds of years, prediction of video quality was thought to be impossible, actually. You'd read papers that said, well, you can't really do it. We don't understand the brain. We don't understand distortions. Let's just use the mean squared error. Okay, and mean squared error is a terrible measure of picture quality. It doesn't predict it accurately at all. Okay? And it turns out the only way to do it is to model distortion at the neural level in the visual brain. Okay? And well, what about deep learning? Well, you can train deep learners to do the same kind of task that I've just described. Of course, now you're talking about a model with millions of parameters instead of like 10, okay, that does the same kind of job. So today, deep models are not being deployed by the streamers like Netflix and Facebook and all these companies. The reason why is because you don't need the deep models for this full reference problem. You've got science instead. Okay, you understand the brain and how it responds to these distortions, and you can make these visual comparisons. In science, like I said to you guys, science is truth, and no deep learning can improve upon the truth. Okay, so that's why these models remain dominant out there in the real world, okay? Streaming to billions of peoples. But nevertheless, we're using deep learning every day. In our today's studies of picture quality, we're even using language models to do this kind of work. And the reason is that you can make picture quality harder. One way is where you don't have a reference. You're just given the picture, like I show you that first picture on, on 6th Street in Austin. It has so many different distortions, all commingled. It's very complicated, and it interacts with the content. We've got various faces and so on. And the models I've just described can't quite do as well as the deep learning engines if they're trained on large databases. Or if you have immersive content, like VR environment, you don't really know where people are going to look. It's another complication. Okay? And you have to account for when I'm looking over here, the rest of the world is blurry because of foveation. Okay? You have to be able to account for that. So deep learning is playing a role in everything we're doing going forward, but not on this original problem. Nevertheless, whatever these deep learning engines are learning, it's learning these fundamental principles of scientific truth. Okay, so that's all. These are companies that support our work and that we work with over the years. And that's a good indication of the end of my talk. Was that an alarm you said? First of all, I thought we were all going to run out because of a fire alarm.
The emergency button.
Emergency button. Is there an emergency?
No.
Okay, good. Okay. So, by the way, I'm going to show another visual illusion just because I'm nuts about them. I show them in my classes constantly. But if you have a problem with flashing lights or anything, do not look at this one, okay? There are certain people with certain conditions where they can, not react well to that. So don't look at it if you know you have that kind of condition. I just want to show it to you. I think this is called The Night It Rained on Lowry or something. You know, it's an amazing illusion, but also I like it because it's actually kind of a statement, a philosophical statement. It shows, you know, people who are walking forward, but they never go anywhere. So you have an illusion that they are actually moving forward and walking, but they're stuck in their lives. They have these dreary jobs. They never get home from the factory or work and whatever. And it's thunder and lightning outside, and it's, you know, so it's kind of but it's an understandable illusion. What's happening is, you know, the visual brain, we can also model motion computation in the brain. Okay, that happens in another area of the brain up here called area MT, mediotemporal cortex. The flashing here, which is symbolically represented by the lightning bolt, which actually isn't bright here, disrupts the motion computation. So the brain, and this is what's revealed by a lot of visual illusion, the brain is trying to fill it in. Okay, this flash occurred. Well, there was motion, there must be still motion. So it sort of fills in the motion, you get this sense of continuous motion, even though there's not. Yeah, sure, you can stare and examine the foot. Oh, I see it's going back. That's my wife. What are you talking about? Sorry, I can't talk right now. So we understand this illusion. Okay, so any questions, by the way? I'll go back to here. Yeah.
So in the natural statistics, you mentioned that if you have an image and you subtract the local mean and divide by the local standard deviation, you get a Gaussian.
Yes.
Gaussian. So can we reverse it? That is, start from a Gaussian noise and multiply by some standard deviation and add an image and get an image, something like what diffusion models are doing.
I was going to say, you know, you can do that, but the number of possibilities is very high order. I mean, just think about the number of pixels in an image. Each one could take 256 values. Well, the number of possibilities is far larger than the number of particles in the universe. Okay, so you're trying to recreate something within that very high dimensional space. So you need it to be guided and trained somehow. And so I would say, well, you need a Gen AI kind of thing to do that. Yeah. But you could certainly use this underlying property, and no doubt the Gen AI is learning that to generate very realistic images, even if you can't see that by looking at the weights in the network. Yeah.
Can you also elaborate a little bit on the neural noise? What exactly it means?
Oh, sure. Well, we just modeled it simply as Gaussian noise. I mean, it's far more, neural noise in the brain, not such a bad approximation to that, okay? The neurons actually have a noisy element to them. But it's kind of a big bag because it could also be imperfections in the optics and everything. So simple model, but if you remove the neural noise term, the performance drops noticeably in all these models, okay? So basically we're just saying, put uncertainty in the model, okay? And then calculate. Then predict quality, okay? And it works better. It's kind of like an old idea called simulated annealing, where you sort of jitter the solution, or, you know, if you randomize a neural network, you know, that sort of thing. It's kind of a similar thing, I would say, but which actually has some connection to what actually happens. Yeah. Mm-hmm.
Regarding you showed some example with that stuttering.
Yeah.
Like with the 24 FPS it was stuttering because there was a higher motion.
Yeah.
And with 60 FPS it was like smooth. But in general in cinema it's generally 24 FPS, right? But even if there's fast motion, like professional videographers prefer to have motion blur in it, so that it feels smooth.
So what we're talking about here is more like television. And so you made a very wonderful distinction there. You're correct. Cinema is 24. By the way, you know, that falls outside our, you know, that we should see flicker from 24 frames per second, by the way. You know, you can draw what's called the contrast sensitivity function of the brain, and you should see flicker, actually. You should actually see that. But they cheat because in the movie theater, they show every frame twice. Okay, so it's effectively 48. That's how they get past the flicker that you'd see in those old movies, okay? So that was a side topic. So cinematographers take great care to avoid stutter. So if you're watching a movie that has action, you know, the camera panning is very carefully centered on the subject, and today, of course, they can do all kinds of post-processing to, you know, reduce things in an after effect. But in sports and things like that, it's just television, and you're going to get stutter. when you're following something very fast. So highly controlled situation where you spend months capturing versus something that's happening right now, real time, where you get stutter.
So my follow-up question was I'm coming back to the cinema or general. I mean, it's a more controlled case where they add these light motion blur or they reduce the shutter speed to get that motion blur and that smoothness.
Oh, sure.
That this blur is, I mean, perceptually, it's not an issue. In terms of if I'm watching a movie at 24 FPS, should not be an issue. It's perceptually better rather than seeing a stutter.
Well, once again, it comes down to control. There's a lot of tricks you can do during capture, during editing, during post-processing, during the whole process of cinematography to produce something that doesn't have visual artifacts because you have time and a controlled setting, But you don't have those knobs and things to twirl when you're capturing something in real time. So again, that's kind of the difference. So you're right. There's a lot of things you can do post-production, if you're creating a movie, or even during production if you're, a savvy director and cinematographer.
So I was thinking in terms of let's say Netflix cinema point of view,
Yeah.
not in terms of sports or anything, but in terms of that, again, still trying to get that smoothness and you will see this Gaussianity there, right? I mean,
Of course.
More perceptually better, even if there is some sort of motion blur in it.
You mean induced motion, intentional motion blur, that sort of thing. That's what I include in these sort of post-process. These are typically very localized kind of things. So that what they're doing is they're doing that because they're reducing some kind of artifact that might, they're trying to Gaussianize it actually, in some sense, because they're making it more naturalistic. They're not specifically measuring against a Gaussian function. They're not doing all this processing and so on. They're trying to create something realistic, photorealistic, that doesn't reflect the distortion of too high a frame rate when somebody's running, say Tom Cruise is running or something like that. But that, in effect, is what they're doing. In fact, in CGI, CGI keeps getting more and more realistic. It's funny, in the graphical community, perceptual theories have not been used much. Even today, I've just graduated to deep learning very quickly. So, however, even the compression community, they didn't really use studies of perception very much. But if you keep finding a way to reduce redundancy, and then you show it to people, and reduce redundancy, and show it to people, and then you find out which is the best one, you're doing a perceptual optimization over the years. And so you've perceptually optimized that way. Which is, of course, very expensive and time-consuming kind of way. So same thing with CGI. You just there's a company called SpeedTree that makes realistic trees. There's another company that does this and does that. And they put them all together. That's why when you watch a movie, the credits is like an hour long, almost as long as the movie, because there's so many different, special effects teams who are at work creating this part or that part of that part of that part of the CGI that you're looking at to create a sense of realism. All together because of all those human minds and all the people who've looked at the outcomes, not only of the development of the ticket over years, but the movie itself, you've perceptually optimized it in that way. So it looks like, it really does look like a real Hulk or something. Yeah.
Going back to the local variance estimation and the normalization.
Yeah.
So if you have a very large field over which your local field is a large field for each of those points, it looks like you might not remove much, but if it is a small one, you might remove much of the content. So somehow there seems to be a trade-off in the choice of the local field for the parameter estimation.
Right. So what you're saying is, so suppose you've got a great big picture, and you take regions over which you're like computing bandpass. Well, the model we use uses multiple, first of all. So if you send it to a shallow network, it picks which one is giving the best against human subjective scores. But what I can tell you is that these statistical models work even if it's picture size. It's much more powerful because images contain local information and they are multi-scale to measure things locally and over scales if you're going to make accurate predictions. But if you take whole predictions and bandpass filter them, look at the histograms, it's going to be Gaussian. And that's what Ruderman did. He didn't look at little, he subtracted over little areas, okay? But he found over whole pictures that the histograms are Gaussian, okay? So it's a global and a local property, both.
So are these models applicable to live transmission versus offline? Because computation, do you have to use different set of models? Like VMAF is for both live and offline?
VMAF, in today's world, VMAF is a trivial computation. It's actually, VMAF is burned into firmware. And, you buy a computer, it's got VMAF burned in there, okay? And it's fast enough for real time very easily. There's another model called SIM, okay? That one is used to control all the real-time transmissions in high definition by British Telecom, and that's real time. Okay, pick the compression parameter in real time based on measurements by a video quality model. Okay, and VMAF is also very fast. Yeah.
One more question. What about 3D video? So are these applicable, or do you have to change?
So we did studies for years. For a while there, we were really working on this. Okay, 3D. And it turns out that these natural scene models work very nicely on the third dimension. They work well on depth maps, actually. Okay, the natural scene models hold with great reliability. So you could use those to make predictions not only of the texture, so to speak, but of the three-dimensional structure. And we did human studies, and we created predictive models. We even had one that everybody liked and won a paper award. But 3D televisions, remember every television for a while there you bought was 3D, and then none were, like next year, So what happened was, people bought the television and they put the glasses on the shelf and they just turned it to 2D mode because, first of all, half the people don't get much from it, the 3D. Another 10 to 12% can't see in the third dimension stereoscopically. Okay, so that leaves, an audience willing to wear these glasses, maybe, it's uncomfortable, and so that research, was there, but it'll come back. Where's it going to come back? VR, okay? So VR is, the hope is, and this is years away, but VR right now is this big old helmet, Everybody buys those and puts them on the shelf too, in the closet and collects dust. But it's coming where it's going to be like the new Facebook Meta glasses, which don't actually have any visual aspect. But they will, okay, where basically, you'll have compute power in the glasses, okay? You'll store things like avatars of your friends in your glasses in 3 dimensions and so on. And so we've been working with Reality Labs on exactly that, quality of 3-dimensional avatars, predicting those. Okay. And a big question is not just the quality, but when you transmit from one part of the world to another, hopefully, put on my glasses, I'm in Texas or I'm in Colorado where I live now, I'm talking to Rajiv in 3D, we see each other in each other's environments, latency. Okay, you've got these issues in transmission latency, compute latency, and all these kind of things. That's a big thing. It can distort, even if its latency is small, it can distort just your facial expression a little bit, such a little bit, but then it becomes creepy. You don't like it, because the mouth is just, a little bit wrong, and that's where it enters what's called the uncanny valley. Okay, you may have heard of that. Where, what was that movie? It was called. Anybody see the Polar Express? Remember Santa Claus? I'm a grown-up, and I was terrified. This guy. And I can imagine kids. This Santa Claus looked too realistic. And he's like 10 feet tall and, all that kind of thing. But not realistic enough. You could tell he was not real, but it was too real. And so people were negatively affected by that. It was in what's called the uncanny valley, okay, where it's uncanny how real it is, but yet it's not. Now, that was originally formulated in the context of robotics. This day is coming where robots are going to be so real, they come up and talk to you just like I am, but something will a little bit off. Won't be quite right, and it'll be kind of scary for a lot of people. It's the uncanny valley. Kind of off topic there, but it's all on topic. Yeah.
Okay, so in the interest of time, we'll stop at this point. Thank you all for attending. I request Rajesh to present a small token of appreciation for visiting us.
Thank you very much.
Thank you very much. Whoa! I got a lot of loot in. I even got a book, and I got something in here. Whoa, man! Thank you very much.
Thank you all.
Thanks for coming.